Welcome back. This is lesson 2 of Unit 1. Today we're going to be analyzing graphs of functions and relations. By the end of this lesson you should be able to use graphs of functions to estimate function values and find domains, ranges, y-intercepts, and zeros of functions. Secondly, you should be able to explore symmetries of graphs and identify whether a function is even or odd. This even and odd here will be on the ACT. Please make note of it. First, let's consider this function. We've got the graph for this function. What they're asking us to do is they're asking us to find the value of the function at 2, 3, and 5. To do that, I'm going to start by finding f of 2. So I move over to 2 in the x-axis, go up, and I see that that value is 1. So f of 2 is 1. Now, I'm going to do the same thing with f of 3. F of 3, when I go over to 3, it looks to be 2.5. And finally, f of 5, when I look at it, I go to 5, I go up, it is 4. Now, this time, we're going to find the domain and range. So, my domain values are all the x values. We found that out in the last lesson. The range values are all the y values. So, when I'm looking at this graph, and I see that this arrowheads tell me it's going to go on forever. It keeps going on not just down but also out. It's going to be going out in that direction forever. So therefore my lowest possible domain value is going to be negative infinity. Now, same thing over here. This arrowhead tells me it keeps going up forever. But not only is it just going up, it's also going out in that direction forever. Therefore, my highest possible domain value is going to be infinity. This also includes the range. We already said that it keeps going up and down forever. So the lowest possible y value I'm going to have is negative infinity. My highest possible y value is going to be infinity. So here's your domain, and here's your range. Now let's do the same thing with this graph. This graph does have some limitations. There's no arrowheads on the ends of these. So this is going to change my domain just a little bit. In this case, my domain, my lowest possible value is negative 3, and we see that there's no open circle. If there's no open circle, then we know that it can be 3 and therefore requires a bracket. The highest possible value is 4. There is an open circle, so I need to make sure that I put a parenthesis. Now for the range, my lowest range value, well, if I'm looking at the y-axis, the lowest one is 0. It can be 0, so I put a bracket, and then the highest possible value looks to be 3.25, we'll say. And that is equal, so I can put another bracket. Okay. Now, the next concept we're going to talk about is x-intercept. The x-intercept is where the function crosses the x-axis. The y-intercept is where the function crosses the y-axis. Pretty simple. Now, if a function crosses the x-axis, then we know for a fact that the f of x, or the y value, has to be 0. Remember this, it has to be 0. Same thing with the y-axis. If the function crosses the y-axis, then we know for a fact that the x value has to be 0. Remember that. So, when I'm looking at this, we're going to find the intercepts here. The y-intercept, well, that's pretty simple. The y-intercept, where it crosses the y-axis, is 4. And the x-intercept, in this case, there are 2 x-intercepts. Another name for x-intercept is called the zeros. I want you to remember that. The x-intercepts for this function are 4, and it looks to be 6. Okay, so we have the y-intercepts and the x-intercepts. Another name for x-intercept is 0. Okay, next concept, tests of symmetry. We have the graphical test. The graph of relation is symmetric with respect to the x-axis. That means you can fold it over the x-axis if and only if for every point xy on the graph, the point x negative y is also on the graph. So let's say this was -2. Or I'm sorry, let's say the x value is 2. And then we have a y value of 2 and a y value of -2. If that's the case, then this is symmetric with respect to the x-axis. To test that algebraically, we replace y with -y, and if we do that, it will produce an equivalent equation. You'll see more about that in a moment. Now, if the graph of a relation is symmetric with respect to the y-axis, then instead of having like this up here, x, y, x, -y, this time we have x, y, -x, y. And when we see that in the picture, it kind of makes sense. It's going to be equal distance from the y-axis in both directions. We get this if we have the equation replacing x with -x, and we'll get the same exact equation after we clean it up and simplify it. If the graph of relation is symmetric with respect to the origin, that means we would rotate the graph around the origin. If and only if for every point xy, there's also -x, -y. We get that algebraically by replacing x with -x, y with -y, and when we do that and clean it up and simplify that equation, it will produce the same exact equation. So let's try this. We're going to show that we're going to analyze the graph, and we're going to say, looking at this graph, we can see that we can tell that it's going to be symmetric around the x-axis or about the x-axis. But we have to show this in more than just this manner. What we're going to do is we're going to put these points down and see if we have a positive y value and its negative y value. So if I put in here 2 for x, when I look at the 2, I'm looking at the 2 value, well, that looks like it's about 1. So I'm going to put a 1. But it's also at -1. And I keep going, and I'll put in, let's say 5, because that's a nice number to look at. And we'll say at 5, we're at 2, but we're also at -2. And then for 10, we're at 3, and we're also at -3. Now we see that for each x value, I have the opposite y values. One was at 1, one was at -1. One was at 2, one was at -2. One was at 3, one was at -3. This shows numerically that this function is symmetric around the x-axis. Now, we're also going to show it not only numerically, we're going to show it algebraically. Now, we saw what the function was. In this case, the function was x minus y, x minus y squared equals 1. Now, according to what we said, we have to plug in a -y for y here. So I'm just going to do that to test it. I'm going to put in -y in place of y. Now, when I clean this up, I'm going to have -y squared. Well, that just gives me y again. So then, y minus y squared equals 1. We started and ended with the same exact thing. This tells me symmetric about x-axis. So now I've shown it graphically, I've shown it numerically, and now I've shown it algebraically. These three things are what you're going to have to do on your homework when they start asking you to prove something is symmetric or show something is even or odd. So let's try another one. So looking at this, we're going to pick some values for x and see where they are on the y-axis. So when I do that, I'm going to start with -8. That looks like a good one. And that puts me at -0.5. And I'm going to pick -2. That puts me at -2. -0.5 puts me at -8. And then 0.5 puts me at 8. 2 puts me at 2. And 8 puts me at 0.5. So when I'm looking at these, what you're going to notice is that graphically I could take this and turn it, rotate it around the origin, and I would end up with the same exact thing that I started with. Okay? So, and we can see that numerically because if I have -8, -0.5, if it's symmetric around the origin, I would have the point 8 and 0.5, and I do. If it's symmetric around the origin, I'd have -2, -2. Also, I would have 2, 2, and I do. And finally, I would have -0.5, -8, and 0.5, and 8, and I do. So this shows you graphically, numerically, and now I'm going to show you algebraically. Now, algebraically, we have y equals 4 over x. Now, in place of y and x, I'm going to put in negatives. So I have -y equals 4 over -x. Now, cleaning this up, because we don't want a negative y out here, we're going to multiply both sides by -1. When I do that, this becomes y equals 4 over a negative cancel, x. Started and ended with the same thing. If we start and end with the same thing after doing this, we know that this is symmetric about the origin because we used a -x and a -y. Okay, last concept, even and odd functions. If I'm looking at an even and odd function, well, this tells me if the functions are symmetric with respect to the y-axis, they are called even. Remember, if it's symmetric around the y-axis, I plug in -x for my x values. Simplify it and check it. If you start and end with the same things, you know it's even. For odds functions, it's symmetric around the origin. For the origin, remember we had to plug in a -x and a -y to get the same function. So let's try that. Let's start with this first function. This first function, I'm going to check to see if it's even, odd, or neither. Okay, so first thing I would do with this, I would put it into a graphing calculator. I would use a graphing calculator and I would see what the picture looks like. Now, after looking at the picture, it looks like it might be symmetric around the origin. Okay, so when me thinking that it might be symmetric around the origin, I'm going to change this around. I'm going to say another name for f of x we said was y. So I'm going to say y equals x cubed minus 2x. Now, I let -y and -x be in there. So -y equals -x cubed minus 2 times -x. Now, cleaning this up a little bit, I end up with -y equals -x cubed. Cubing -x times -x times -x gives you -x cubed. And then I get -2 times -x. That gives me a positive x. 2x, positive 2x. Now, I don't want this negative out here, so I'm going to divide both sides by -1. And I've got y equals x cubed minus 2x. If that's what we started with, then you know that this is symmetric about the origin. Now, let's check this one. G of x equals x to the fourth plus 4. I'm going to check this. I'm going to graph it. I'm going to look at it. Graph it in a graphing calculator, look at it. It looks to be symmetric around the y-axis. So if it's symmetric around the y-axis, I'm going to plug in negative x to see if this works. If I start and end with the same thing, I know it's symmetric. So g of negative x equals negative x to the fourth plus 2. Okay, negative x times negative x times negative x times negative x, that gives me x to the fourth plus 2. Did I start and end with the same thing? Yes, I did. Therefore, this must be symmetric around the y-axis, and therefore it is an even function. So this was odd function, even function, and now let's check this one. I bet you guys are thinking it's going to be neither. Guess what? You're right. But let's show it. So I'm going to start by graphing on a graphing calculator. Now, when I first originally graphed this, it looks to be symmetric around the origin. So I'm going to plug in negative x and negative y to see if it works. So remember, I'm going to change this to y equals x cubed minus 0.5 x squared minus 3x. So then negative y equals negative x cubed minus 0.5 cubed minus 0.5 negative x squared minus 3 times negative x. Now we just clean it up. Negative y equals negative x times negative x times negative x. Well, that's still just negative x cubed. Okay, then we got this negative x times negative 0.5x. Wait, we got negative x squared. So that gives me x. So that means that this has to be negative 0.5 x squared plus 3x. Now, dividing both sides by negative 1, I end up with y equals x cubed plus 0.5 x squared minus 3x. Did I end up with what I started with? And the answer is no. If I didn't end up with what I started with, and when we looked at the graph, there's no way we could tell. We knew that it wasn't going to be even because the graph didn't even look close to that. So we're going to say this is EITHER. Okay, for further clarification, please see the PowerPoint. If still stumped, bring questions to class tomorrow. Thank you very much, guys, and good luck.